Okay, this tutorial will be solving for heat of a reaction using a calorimeter. In this particular problem, it's a heat of combustion problem, so we'll be using what's called a constant pressure calorimeter. This is also known as a bomb calorimeter. Okay, and we're going to just simply apply the steps from the previous tutorial in solving this. So first it says write a balanced equation, calculate the reaction enthalpy. So I'll write my balanced reaction up here. So it says it's burning in excess oxygen, and the products of combustion of a fossil fuel like this would be CO2 and H2O. So to balance, we'll have 6 carbons, 3 there, 12 plus 3, let's see, 12 plus 3 is 15, so we need to do 15 over 2, so I'm going to just put 15 there, a 2 there, and then change that to a 12 and that to a 6, so it should be balanced. Okay, so let's start this problem. So the first step was to calculate Q of the reaction. And for a bomb calorimeter, there's 2 equations to use. For a bomb calorimeter, the heat of the reaction is equal to Q reaction C for the calorimeter times delta T. So notice there's no mass. It's because it says it's a calibrated constant pressure calorimeter. Calibrated means the entire mass of the calorimeter itself is factored into this number. So you'll see that the mass is absent in our normal heat from our normal heat equation. So anyway, this will be equal to C calorimeter times delta T. So C for the calorimeter, the heat capacity of the calorimeter is this. That's C. Okay, this we're going to save this for. So let's take a step back for a second. We're going after this number, the heat of the reaction. And our final units are kilojoules per mole. Okay, mole of whatever burned. Mole of, we could generalize this, mole of system used. What's our system? This reaction, that's our system. So this mole amount, or it's grams, which is as good as moles, is going to go here. So we're saving that number for the end. Okay, so Q for the calorimeter is 551 joules per Celsius times the change in temperature. So it says the temperature rose by this number. So they're not giving you TI, they're not giving you TF, they're actually just giving you delta T already. So 8.60 C. So I get 4.74 times 10 to the third joules. Okay, and this is the heat that was absorbed. So notice that the temperature rose. So from the surroundings perspective, it gained heat. So that would be a positive number. So on to step 2 is step 2 is to put it in terms of the system. So step 1 is the surroundings. Step 2 is put it in terms of the system. So we say that the heat that the calorimeter absorbed is equal to the heat released by the reaction, or as always, the reaction is the actual system. So we flip the sign. Step 2, always flip the sign. So whether step 1 was endo or exo, you just flip the sign, times 10 to the third joules. Okay, step 3 is to put it in terms of kilojoules per mole. So I'm going to use some dimensional analysis and go 4.74 times 10 to the third joules, and say in 1 kilojoule there are 1,000 joules. Okay, and I'm going to put 1 over the, or let's see, how do we get moles on the bottom here? Actually, I'm going to go back here and just divide by the grams or actually, you know, I could do it in 2 steps. So I'll just go like this, 0.113 grams of benzene. Okay, and there are 78.12 grams per mole of benzene. Okay, so my joules cancel, okay, and then my grams of benzene cancel here. So now I am left over with kilojoules per mole. Okay, and so we get, all right, that's the end of the problem. So we get negative 3,280 kilojoules per mole of benzene. So step 4 said if it's necessary, so in our balanced reaction it's actually showing 2 moles of benzene react. So this is showing per 1 mole of benzene. So let's see. Actually, this should still work. Okay, so in part B, it says if you burn 3 grams of benzene, how much heat is given off. So in step 3, we need to actually double this number to make it per 2 moles of benzene. This was actually step 4 from the tutorial. So it's 2 times negative 3,280. Okay, so this would be this would be 3280 times 2. So this would be 6,560 kilojoules per 2 moles of benzene. So what this means is now I can write that after my balanced reaction. I could write it here because this is showing per 2 moles. So I write the number negative 6,560 kilojoules. Okay. So if you burn 3 grams of benzene, how much heat is given off? So the magic of this number is it allows us to, once we have this number, this is like a set number for this reaction. So you'll see that enthalpy or heat changes for reactions are specific for whatever reaction that it's for. So if we have 3 grams of benzene, okay, and we want to know how much heat is given off, we could use our conversion factor up here, that this much heat is released per 2 moles of benzene. So we change this to moles. So 1 mole of benzene is 78.12 grams. Okay, and then we use our new conversion factor that we got from part A. So this is 6,560 kilojoules per 2 moles of benzene. So our grams cancel and then moles cancel. Okay, and then we should get heat here. So 3 times 6,560 divided by 2. So we get 9,840 kilojoules of heat given off. You might ask what happened to my negative. I just say heat given off, okay, and that kind of takes care of the negative sign so that we know that heat was given off in the reaction. Okay, that's the end of our tutorial.